Alright everybody, welcome to video lesson number 3. This lesson is for Monday. We will be having a work period Monday, so that if any of you have any questions on anything from the last 3 lessons from Thursday, Friday, or this one, you will be able to ask me and use the time to basically get help with anything that you didn't understand from those lessons. Today we are going to be looking at we're going to start looking at the actual equation of an exponential function and look at what the graph of that function looks like. So first thing we're going to do is we have these table of values with equations at the top. We're going to find out what each of those are equal to. So the first one here is f of x equals x. So essentially all of these f of x values are equal to the x value. The second one, b, we have f of x equals x squared. So we're squaring all of those values, and this is kind of the basic parabola that we looked at. So we know it's 4, 1, 0, 1, 4. Keep going. We have 2 to the negative x, 2 to the x, so the first one, 2 to the negative 2, or 1 over 2 squared, which is 1 over 4. Next we have 2 to the negative 1, or 1 over 2, so 1 half. 2 to the 0, remember anything to the power of 0 is 0. 2 to the 1 is 2, and 2 squared is 4. This last one we have 0.5x, or 0.5 is also 1 half to the power of x. So what we have is 1 half to the negative 2. We flip that reciprocal because the exponent's negative, so it becomes the 1 over 2 becomes 2 over 1, or just 2 squared. We have 1 half to the negative 1, or 2 to the 1, or 2. And if you look over, you can see this is actually just the opposite of the one that we have on the left of C. So we end up with the same numbers, but in the reverse order. So we are going to graph these now. Now, C and D are what we call exponential. And we call them exponential because the x is actually in the exponent. And that's kind of the definition of an exponential function, is one in which the exponent is the variable. What you'll notice, to go from 1/4 to 1 half, we multiply that by 2. To go from 1 half to 1, we multiply it by 2. And so on, and that pattern always works. To go from 4 to 2, we multiply by 0.5. 2 to 1, we multiply by 0.5. And again, that always works. So what we say, when we do that division, essentially what we're doing is we're taking the x value and we're dividing it by the x value above it. So here, for example, we will be taking the y value, and dividing by the y value above it. So 4 divided by 2 gives us 2, which means we're multiplying the 2 by 2 to give us 4. Same thing here. We're taking the y value, 1 over 4, dividing it by the y value above it, 1 half. If we have 1 over 4 divided by 1 half, it's like saying 1 over 4 times 2, or 2/4, or 0.5. So we call this, or we say that these have the same ratio, or in other words, they have a common ratio. And if that's the case, that is the check. If you ever have a table of values, that's the check you can do to see if something is exponential. look for that common ratio, and if they're the same for every single one, then your table of values represents an exponential function. Another way to think of that common ratio, essentially what you're doing is finding the first differences, but instead of subtracting, or I should say it's just like finding the first differences, but instead of subtracting, you are dividing instead. So, we're going to graph this. We have, actually we need that to be farther in the middle. We have -1, -2, 1, 2. We have 1, 2, 3, 4. So the first one, A, was just f of x equals x. So 0, 0, 1, 1, 2, 2. We could keep going 3, 3. So that is our A. Again, that's a straight line. The next one, we have f of x equals x squared. So maybe we'll use different colors for these. B, we have 0, 0, 1, 1, 2, 4. Same thing on the other side, -1, 1, -2, 4. Graphing those, we get that parabola, which we should have known because the equation was f of x equals x squared. C, we have 2 to the x. So -2, we had 1/4. -1, we had 1/2. 0, we had 1. 1, we had 2. 2, we had 4. And essentially, we're going to draw a nice smooth curve through all of those points. So that blue one is our C. And the last one, we'll do in green. Again, it's basically the same numbers as C, but in the opposite order. So at -2, we had 4. -1, we had 2. 0, we still had 1. 1, we had 1/2. And 2, we had 1/4. So this green one is our D. F of x equals 1 over 2 to the x. So you can see the red one's the parabola, which we should know because it's x squared. The A, the black one, is a straight line, which again we should know because it's just f of x equals x, or y equals x. C and D have what we call that exponential curve because the exponent is the variable, so the exponent is the x. So to summarize this, what we have is for an exponential function in a table of values, again we call those the common ratios, or equal. It's similar to the first differences, we could also call them the first ratios, but in order for this to be exponential, if we have our points lined up from smallest x value to biggest x value, and we take the y value and divide it by the one above it, if we get the same thing every time, like we have here and here, so for D we were multiplying by 2 every time to get the next y value. For sorry, that was for C. For D we were multiplying by 0.5 every time to get the next y value. We call that a common ratio. If you have that common ratio, then that means we have an exponential function. The graph of an exponential curve will always have an asymptote, and that asymptote will always be a horizontal asymptote. So depending on where that graph is, it could look like this, for example, and we would have a horizontal asymptote that exponential is never actually going to touch. Even if it was decreasing, again, we would have a horizontal asymptote that the graph gets very, very close to but never touches. It may look like, a lot of these graphs will look like they have a vertical asymptote as well. They don't. It's just that the graph is increasing by so much each time. Say we're multiplying by 5 every time, that number would get bigger and bigger quite fast. So it just looks like it has a vertical asymptote, but it doesn't. It will always only have a horizontal asymptote. The equation for these can be written in the form y equals a times b to the power of x, where a represents the initial value, or the y-intercept, and b is that whatever that common ratio is, that is going to be your base, your b, which we call the base. Now the initial value is only the initial value as long as there's nothing added or subtracted on the end. So in that equation, a, b to the x, there's nothing added or subtracted on the end. We are going to look at equations later on where there is something added or subtracted, and there's something else that we have to do to find the initial value. Now, what we need to look at is when b gets bigger than 1. So, for example, C. For example, C above, the graph exhibits what we call exponential growth. And what that means is that the graph, as we go from left to right, so as our x values get bigger, that exponential graph is growing, or it's getting bigger and bigger and bigger. When 0 is less than b, which is less than 1, or in other words, when b is between 0 and 1, the graph exhibits what we call exponential decay. Or in other words, again, as we go from left to right, as our x's get bigger, our graph is getting smaller and smaller and smaller. So, what we have here is we want to determine whether the following table of values represent functions which are linear, quadratic, exponential, or none of the above. To do this, we need to use a few things to see whether it's linear, quadratic, or exponential. If it's linear, the first differences will be the same. If it's quadratic, the second differences will be the same. If it's exponential, it's going to have that common ratio. So, for example, it should be pretty easy to look at something and see if the first differences are the same. If the first differences are the same, it's either going to be increasing or decreasing by the same amount each time. So for this first one, first differences, we're taking the y value, subtracting the one above it. Because there's nothing above this 13, we don't have a first difference for that one. The next one, we have 10 minus 13, or negative 3. Then we have 11 minus 10, or 1. If we keep going, we have 16 minus 11, or 5. We have 25 minus 16, or 9. And finally, we have 38 minus 25, or 13. So we can see there, first differences aren't the same. What we're going to try next are the second differences. Second differences, we do the exact same thing, but instead of using the y values, we use the first differences. So there's nothing in that first one, we don't have one. There's nothing above that next one, so we don't have a second difference there. And then we work from here. So zooming a bit, we have 1 minus negative 3. If we're subtracting a negative, it's like adding, so that's 4. We have 5 minus 1, which is 4. 9 minus 5, which is 4. And 13 minus 9, which is 4. So what that tells us is second differences are all equal. Therefore, that table of values represents a quadratic. For this next one, you could do first and second differences. What we can see is that if we do 72 divided by 144, we get 0.5. So that means that 144 times 0.5 is 72. If we keep going, 36 divided by 72, 0.5. All the way, 36 is 0.5. 9 divided by 18 is 0.5. 4.5 divided by 9 is 0.5. We have common ratio. Which means that that table of value represents an exponential. The last one we have here is C. If we look for the first differences, again, there's nothing above that 49, so we don't have anything there. Then we have 40 minus 49, so we're taking the y value, subtracting the one above it. It gives us negative 9. 31 minus 40, negative 9. And if we keep doing that for all of them, we get that all the first differences are negative 9. So what that means, first differences are equal, therefore it is linear. So using just the first differences, the second differences, and seeing if there's a common ratio, we're able to show that whether that table of values represents a quadratic, an exponential, or a linear function. The next one, we want to be able to look at graphs and determine essentially the same thing. Is it quadratic? Is it exponential? Is it linear? And if it is exponential, is it an example of growth or decay? So with the graphs, essentially what we're looking for is what we call the exponential curve. And I'll draw this off to the side. The growth curve, again, is going to, if we have our grid, it's going to start small and get bigger and bigger and bigger as we go to the right. The decay curve is going to start big and get smaller and smaller and smaller as we go to the right. Both of those would have that asymptote that the line is never going to cross. Now what you'll notice is that both of those kind of open up, or they curve. The curve is opening in the positive direction. It's opening up, as opposed to something like this one, letter C, where that curve is kind of opening down. So in order for it to be an exponential curve, it has to be opening up. If we look at these examples, the two that we see that do this are A and C. So those two are exponentials. That exponential curve, once we've identified it, we need to determine is it growth or decay. We're just looking at the graph and looking at, as we go from left to right, does this curve go from small to big, or does it go from big to small? In A, the curve goes from small to big, so that curve is getting bigger and bigger and bigger. Therefore, we have exponential growth. C, we said, is the other one that exhibits that exponential curve. So it's going from big to small, but in a curve, not in a straight line. So what this one is doing is we have, again, exponential curve. It's going from big to small, or in other words, what we call exponential decay. Now we want to look at the other ones and explain why aren't they exponentials and what they are. This one here, B, is a U-shaped graph, which we call a parabola or quadratic. C is not something we're going to be looking at in this course, but it actually looks like it's kind of a flipped exponential. But because it's flipped, we don't call it exponential. This is actually I guess maybe flipped isn't the right word, it's the inverse of an exponential, which we call a logarithm. Again, we're not going to look at logarithms in this course. You will look at it in grade 12, but that is essentially what the graph looks like. It looks a lot like an exponential, but the asymptote in this case is a vertical one, whereas again with an exponential the asymptote would be a horizontal one. So that's an HA, that's a VA, and that's a good indication of whether or not something is exponential. Again, it has to have a horizontal asymptote, not a vertical asymptote. D and F are those sinusoidal graphs that we looked at last unit. On top of these graphs, we also have to be able to look at an equation and identify it as exponential or not. So doing that, again, we're just going to look at it, say whether or not it's exponential and why it is exponential or not exponential. This first one is, we have that 3x squared minus 5x, so the x isn't part of the exponent, it's the base. That first one is actually a quadratic in standard form. So it is not exponential. If we look at B, now the variable, the x, is in the exponent. When your x is in the exponent, that is what makes something exponential. So for us, g of x is exponential. Same with h of x. Even though there's that x minus 5 in the exponent, there's still the x. So that variable is still in the exponent, which also makes it exponential. Again, same with d. Even though the variable is negative, so it's negative x, again, it's still in the exponent, which means that it is still exponential. We're going to look at how these differences, making the x negative in the exponent, subtracting 5 like we are in C. We're going to look at how these affect the graph, and these are actually the transformations that we've been looking at before. But what we have to remember is, as long as that variable, as long as the x is in the exponent, it is an exponential equation. E is a sine equation or sinusoidal function. So not exponential. And again, F, x is not in exponent, so it is not exponential. So we've identified which ones were exponential, which was B, C, and D. What we need to do now is identify which of these are exponential growth and which of them are exponential decay. So in order to see the exponential growth, what we need to do is look at the b, or the base, of our functions. This first one, our base, is equal to 3. 3 is bigger than 1, and if your base is bigger than 1, what we have is exponential growth. The next one, we have b equals 0.1. 0.1 is between 0 and 1, and when your base is between 0 and 1, you have decay, exponential decay. Now, the only problem with D is, in order to determine if something is exponential growth or decay, what we need to do is make the exponent positive. So I'll write that down. Again, to determine growth or decay, exponent must be positive. So what we're going to do is use what we know about our exponent laws to make that exponent positive. If we have g of x equals 0.3 times 2 to the negative x, that's like saying 2 over 1. And if our exponent's negative, like it is here, we have negative x, what we can do is flip that base and make our x positive. So this is like saying 0.3 times 1/2 to the power of x, which makes our base 1/2, which is between, so 0 is less than or equal to 1/2, less than 1, that base is between 0 and 1, which means we have decay. Finally, a couple more things. We want to look at the y-intercept. The y-intercept of any exponential function can always be determined by setting x equal to 0. So if we want to find out what all of these y-intercepts are for the exponential functions above, again, all we're going to do, if we start with b, is set x equal to 0. 3 to the 0 is 1. That one is 4. For c, again, we're going to set x equal to 0. We have 0.1 to the negative 5. 0.1 to the negative 5 is 100,000. Then times 4 gives us 400,000. And finally here, I'm just going to take the equation that we changed to 2. So we have g of 0 equals 0.3 times 1/2 to the 0. Again, anything to the 0 is 1, and that one is equal to 0.3. So find the y-intercept, not too bad. All we're doing is setting y equal to 0. And finally, the last thing we're going to look at is the domain and range. With domain and range, domain can essentially, you can pick any value of x and put it into an exponential function. So there usually isn't any restrictions on the domain. The only exception is if we're dealing with application questions. For most application problems, when that involve exponential functions, the independent variable will be time. We can't have a negative time, so usually it's restricted as being t element of R such that t has to be greater than 0. Again, we usually cannot have a negative time, so we just have to make sure t is positive. Actually, it's t greater than or equal to 0. The range of any exponential function is always restricted to the values above the asymptote. That asymptote, what we're going to look at later, is going to be above the asymptote y equals c. So essentially tomorrow we're going to be looking at transformations where there is a c value. It's a number that's added to the end. That whatever that c value is, that is our horizontal asymptote. Again, the asymptote is always a horizontal one. Again, so we want to state the domain and range for each of those functions above. Essentially for all of them, we have the domain is, they're not application questions, so for all of them our domain is equal to x element of R. Essentially x can be anything. All of those have a positive a value. There is nothing added on to the end, so the asymptote is y equals 0, and essentially we have our range being y element of R such that y is greater than 0. Now notice it's not greater than or equal to 0 because an asymptote can't be touched. All those asymptotes are at 0, which means that none of our graphs can actually equal 0. So that's the end of the lesson. Again, not too many questions for homework. Tomorrow will be a work period, Monday will be a work period to ask me questions on any of these video lessons or anything from the lessons that you didn't understand. Our test will most likely be next Monday, so a week from Monday. Again, if you have any questions or you think that I made a mistake, put it in the comments, let me know, and I will try to answer it as soon as I can. See you Monday.